Gay-Lussac's law is very similar to Charles's law in one way, and that's because it's a direct relationship. In Gay-Lussac's law, we are talking about the relationship between temperature and pressure. This is going to be involving it's going to be involving rigid containers. This is because volume doesn't change, okay? If the temperature increases, the pressure inside the container increases, and if the temperature decreases, the pressure inside the container decreases. This is a direct relationship. You can see down here, I don't know if you can read that, but this is temperature, and as temperature increases, the pressure is also increasing. So temperature increases, pressure increases. That's a direct relationship. When the temperature is increased, this is the reason that happens. When the temperature is increased, gas molecules move faster. They collide with the container walls more frequently and more forcefully. Think about if you were running around in a room versus if you're just walking around in a room. You're more likely and more frequently going to run into something, and you'll hit it a lot harder, right? That's the concept of temperature being higher. It makes the molecules move more quickly. They hit the walls more frequently and more forcefully. That means the gas pressure inside the container increases since the container has rigid walls, and the volume stays constant. Okay, so rigid walls means volume is constant. Volume won't change. When the temperature is decreased, just the opposite. Gas molecules slow down. They hit the walls less frequently, less forcefully. That results in the pressure being lower. And again, it has to have rigid walls. The volume has to stay constant. Okay, volume has to remain constant for this law to really be observed. Okay, here's Gay-Lussac's law in equation form. It's P1 over T1 equals P2 over T2. It's a direct relationship. As one quantity increases in value, the other quantity also increases, and vice versa. We can talk about T1 and T2. Remember, they have to be in units of Kelvin, not Celsius. So again, we're going to add 273. The amount of gas and the volume have to stay constant. But again, T1 and T2 have to be in Kelvin. P1 and P2, their units just have to match. Here's some real life examples. Popping popcorn. If you put popcorn in the microwave, or or if you just have it in a pan, you heat it up, the pressure builds inside that kernel until it explodes. That's the way popcorn works. Throwing an aerosol into a fire, an aerosol can into a fire could cause it to explode. That's because there are molecules inside the aerosol can, and if you throw it in a fire, the pressure builds up to the point that rigid container can't hold it anymore, and it will explode. Let's go ahead and do a mathematical example of this. So we have a gas with a pressure of 699 millimeters of mercury at 40.0 degrees Celsius. What's the temperature at standard pressure? Now, if you recall, when we talked about standard temperature and pressure, standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. Okay. Now, here's the key. We have to have the same units of pressure. Right now, I have millimeters of mercury over here, but I have 1 atmosphere. So we want to know that conversion factor. You can find the conversion factor on the back of the periodic table, the second page of the PDF of the periodic table. 1 atmosphere is equal to 760 millimeters of mercury. Okay, so that's the second pressure. So what is the temperature? P2 at standard pressure, that would be P2. P2 equals 760 millimeters of mercury. Okay, and then I've got T1 and P1. We want to go ahead and plug these numbers in. So we have P1 as 699.0 millimeters of mercury. T1 is 40.0 degrees Celsius. Don't forget, anytime we're dealing with temperature and gas laws, we've got to add 273 if it's in Celsius. We've got to have it in Kelvin. And then P2, again, that was 760 millimeters of mercury. And that's an exact number, so I could go ahead and make it match the number of sig figs of that. It's standard pressure. And then our temperature, T2, that's what I'm looking for. I'm going to try to find that in Kelvin because that's the easiest unit to use in gas laws. It's the easiest unit to find. So if they don't ask you to convert it into Celsius, then we won't, because it's much easier to leave it in Kelvin. So I just added 40.0 plus 273 to find what T1 is. It's 313.0 Kelvin. All right, we just found we have P1, T1, P2, and we're looking for T2. So I'm going to solve for this. P1 is 699.0. Remember, it's P1 over T1 equals P2 over T2. That's our equation up here. P1 over T1 equals P2 over T2. So I have 699 over 313.0 equals 760.0 over our unknown, which is T2. Now this is a little bit more tricky than some of the other problems that we've seen, because my unknown is in the denominator. And if you remember in algebra, you can't really solve an unknown that's in the denominator. So we need to get it out of the denominator. Best way to do that is to multiply by T2 on both sides. You could say we'll cross multiply. That's probably what you're more familiar with. So since it's in the denominator, I'm just going to cross multiply and then we'll solve for it. So I have 699.0 T2 equals 313.0 times 760. Decimal right there. So what I want to do now is get T2 all by itself. I've got this number right here that I need to get rid of. I'm going to divide both sides by 699.0. That cancels out. So T2 is going to be equal to 313 times 760 divided by 699. When I do that, I get 340.3 Kelvin. And if we were asked to convert back to Celsius, we would just simply subtract 273 from that number. We're not asked to do that here. All right, Avogadro's law. Avogadro's law says that if the amount of the gas in a container is increased, the volume increases. If the amount of gas in a container decreases, the volume decreases. So we're talking about putting more gas in or taking more gas out. An example of this would be like blowing up a balloon. Okay, so when the amount of gas is increased, there are more gas molecules inside. That increases the number of collisions with the container walls because there are more gas molecules. So the pressure inside the container increases for a little bit until the walls expand so that you end up having the original pressure value once again. You can see from our graph, as the number of moles or the amount of gas increases, the volume also increases. It's a direct relationship. Here's our equation. Avogadro's law is V1 over N1 equals V2 over N2. Again, pressure and temperature are going to be constant. N has to be in moles. Okay, so that's maybe not written right here. Pressure and temperature our constant N must be in moles. So make sure that you know that N has to be in moles. It can't be grams. You've got to convert it to moles if it's not already in moles. This problem gives it to us in moles. So I'm looking for V1, N1, V2, and N2. So we want to label these. I have a volume, and it tells me the number of moles that we have. The volume of the balloon increased to this new volume. Okay, that looks like that's a V2, which means this must be V1. This must be N1 because I want to know how many moles of helium are in the balloon after that change takes place. So N2 is what I'm looking for. V1 is 0.505 liters. N1 is 0.989 moles. And V2 is 0.525 liters. All right, our equation V1 over N1 equals V2 over N2. And we can plug in those variables. Now, V1 is 0.505 over N1, which is 0.989, equals V2, 0.525 over N2, which is our unknown. Again, we're going to have to cross multiply because N2 is in the denominator. It's not where it needs to be. Or if you'd rather think of it as multiplying both sides by N2, you could do it that way too. I end up with 0.505 N2 equals 0.989 times 0.525. Then I want to divide both sides by this 0.505, which is what's being multiplied by N2. When I put that in my calculator, I get 1.03 moles. Remember, N is in terms of moles.